Okay, good afternoon. Yeah, you're most welcome to the Tech Hub, and today we are going to be doing a paper review. So, previously in other videos, we have been doing interpretable machine learning techniques for student performance prediction. We are trying to build a machine learning model that is able to predict if students are going to pass or fail. Yeah, something like that. My name is Semwanga Trevor McDaniel, and my details are over there. So, to start, these are literally the reasons why we are doing this. In order for us to be able to do successful machine learning, successful machine learning um, models, we are supposed to try out what other people have done in their past work. So that is what we are doing in this video. We're going to do a paper review, check out the experiences of other people so that we get the best models to select that. We get the best techniques to select while um, building our models, and to be able to build the best models out of it rather than us beating around bushes. So the paper that we are reviewing is called a novel pipeline for student performance prediction, and we shall be focusing on multi-topology graph neural networks. These are the authors, Ming Li. I guess they were like Chinese people, but yeah, let us get started. Those are the keywords in the presentation, so it's going to be something like we're going to get a lot of graph neural networks, student performance prediction, educational data mining, which is as simple as getting students' data, something like that, and extracting meaning out of it, then a pipeline. So, to start, let us get into the computational problems. Now, an introduction is that um, we are going to focus more on the multi-topology graph neural networks, and we are going to look at its computational problems. Now, before we go into it, we are going to have a look at all the other related work. Now, if you are to look at the work of other people, we have people who have tried out these things. I can see there is a student's early performance prediction. This one used artificial neural networks. That was in about 2013, and all the other things. So people have been doing these things again and again. And the reason for this paper is that it is also picking out it is highlighting out the features that they identify the most, that they can be able to improve and build a better model. So if you are to look at the models or the techniques used on this site, some people use logistic regression, which have an idea of support vector machines and all that, neural networks, naive Bayes. But in this review paper, we are going to be doing a multi-topology graph neural network. So if we are to start, I can say that this is the pipeline. I don't know if you remember that keyword. When we are doing this model training, we first start by collecting the data. Then after collecting the data, we do pre-processing. We do data cleaning. This is where we do the exploratory data analysis to actually pick out the fields that we need in order to build better models. So data conversation, data attribute selection, it is all done at the data pre-processing level, and then we move on to the next level, which is the graph construction. Now here we are constructing topologies, because we are doing what? We are doing multi-topology graph neural networks. So we do um, we do the graph construction. We use what they call similarity learning, because according to the writers in here, they believe that a student's performance is affected by other students' performance, probably his friends or the people that they work with, their discussion groupmates and things like that. So we shall see that in the future. Then after that, in the next step, we get to multi-topology graph neural networks. This is where we make the topologies, um, and yeah, we make the different graph neural networks, and then that is what we are going to use in our prediction. So we make kind of many. It's more like how random forests work. We are going to generate very many topologies, and yeah, we are going to pick, we are going to base on their predictions to have our final answer, and that is what we are having in this slide. So yeah, to proceed, um in the computational problem, if you are to look specifically, I can say the computational bottleneck lies in the computation of the engine decomposition of the graph Laplacian L, which is required for the graph convolution. So the computational problem of this lies in the engine decomposition of this thing. So when we are coming up with graphs, there is something we have called engine values and engine vectors, and the computing of these values is expensive for large scale graphs with hundreds and thousands of nodes. Now in our work here, we are going to find out that every student will be represented as a node, and if you are to look at the real world problems where we are going to be having like universities, we actually have very many students. So because computing these values is expensive, that becomes a computational problem that we kind of have to solve. And then the only way to solve this um, is to try out oh sorry, on the line, yeah, the answer is here. To reduce, we kind of use a polynomial approximation for the spectral filter. So instead of going with the first one, um, with using the diagonal matrix where we get the engine values and vectors, we end up using a polynomial approximation. Though this comes with some trade-offs, we kind of get models that are not so accurate when we use this, but you can balance up the two so that you can be able to perform and get the best results. So if you are to look at the thought process of the writers, like they did their own thinking to be able to come up with this model, and if we are to start, we can say every student is a node, like I said before, and the node is labeled with the student's grade category. If the student, like we mean like, so we are doing um, to like break it down, we are doing supervised learning, and for supervised learning we label that data. So we are labeling the data with a pass fail and a withdraw for every student, and then the node contains the attributes of that student. So can be like their quiz marks, their education context, their behavior, attendance of classes, and things like that. And these factors are all relevant to predict the performance of a student. Now next one. So according to the writers, a student's performance is affected by other students. Feel like one student could perform highly, maybe because he's in a good discussion group or he has good friends and all like that. So the relationships are shown using ages. So that is why we are using neural networks in the first place. We are having nodes as students and ages as the relationships between among those students. And then the graph can be expressed in terms of this, where there are vertices and edges. The vertices represent n students. The more number of vertices you have, those are the number of students you have, and they are edges that connect the two students. And now if you discover, because we are connecting, we can't just connect any person. That is why we end up using similarity learning. We connect the students among themselves after figuring out similar features among them. So in practical problems, this can be described in different ways or from different angles, and to better mine the complex latent relationship between students, we construct multiple graphs. Like we cannot use just one graph to be able to establish the relationship between students, so we construct various graphs, more like how random forest works. We give it special attributes so that it can construct the relationship, and in the end of the prediction, we are going to base on all those different topologies that we are building to get our final prediction. So if you are to look, we are going to develop with three topologies: cosine, Pearson, and Tamimoto. This is what we are going to use in our topologies. These are the topologies that we are going to use. Yeah, if you are to look at the models developed, we are going to first compare with the pass and the withdrawal. Then in another one, we are going to compare with the pass and fail. So if you are to look at this one where the original node embeddings, you can see that the model didn't do well, but after we gave it land data, it was able to classify, and this is for the multi-topology graph neural network. And same goes for the pass fail. So this is for the pass fail, where the other one is for the withdrawal. Now, let us go. So if you are to look at the performance of similar models, you will find out that um, the multi-topology graph neural network actually beats all the models that were used before. So the simple vector machines, the logistic regressions, if you are to look at the accuracy, F1 score and the recall, we can say that this model gives better results and it can be taken on. And for the thing before, that was for predicting at-risk students. And when we did that, when the writers did the study again, comparing with others for early prediction of students, you find out still the multi-topology graph neural network did a better performance. So yeah, this paper review has been about um, about that multi-topology graph neural networks. And you can find this paper and read through it in the description. Link is going to be in the description. Thank you for listening. Have a good time.